introducing all of yourselves. We are representing the RV and the School of Engineering on our WaterWagon project. My name is Peyton. I'm the project manager, and I will be talking a lot about some improvements towards the end that we would like to make on our project, and also a lot of the testing that we did on our project. Bailey will be doing our introduction. Justin will be doing a lot of the pictures that we have on our presentation. Ante will be going over our 3D models and designs, and then Kinsey is going over our bill of materials, budgeting, and then system fabrication methods. So over to Bailey for the introduction.
So what you see in front of you is the outline of our presentation. We'll be discussing 4 main topics: the project overview, the design, the system fabrication, and the project finalization. Each of these topics has little subsections with them, but it would be counterintuitive for me to just read them to you. This will be what we will be discussing today. And on the project overview, we had 4 phases, 2 phases in last semester before our break, and then 2 phases this semester. In phase 1 and phase 2 is really getting the groundwork laid out, doing a lot of research, kind of figuring out where and what we need to do with this project. Phase 3 and 4 took part in this semester. We finished phase 3 after our last presentation. And so now we start phase 4 and we finished building and testing. So now we're currently redesigning a little bit and then currently communicating our results back to you. Our motivation for this project was thinking environmentally green. But we didn't want to just think green, we wanted to also do it safely. Safe in the sense that we can use this and move it so it's safe for everybody involved. We also wanted to have high water quality, and so that also played a part in the materials we use. And conservation, we didn't want to have a big leak or lose a lot of water and be very wasteful on what we did. This right here is a survey question from our survey in the first phase. We use this to gauge interest in the big scale model of our WaterWagon. And as you can see, about 66 people said they would be highly interested in this system. About 32% said they'd be somewhat interested, and 2% said they would be not interested. Then this was out of 100 people. Our design requirements, we have 6 of them. They came from phase 1, which really came from the letter that was sent initially. So we have water quality, mobility, truck connectivity, information and outreach, a cooling system, flow measurability for the conservation, and just making sure that we don't lose anything. Now we used those 6 designs to come up with 10 designs. Each member of the team created 2 of their own, and we narrowed those down to the top 2 designs. These designs are very similar, except that one key difference is that the bottom design does not have a shell around the outside. It would just be the tanks. And the top design has a shell around the outside. To choose between these designs, alternative design 1 is the one with the shell, by the way. So alternative 2 is the one without the shell. And to choose between them, we use this decision matrix. This decision matrix works by taking the relative importance and multiplying it by the number of pluses in the columns below alternative 1 and alternative 2. When we did the math, we saw that alternative 1 had 62 pluses, so that's the design we look like. Next is Ante.
Thank you, Bailey. So as you can see, this is our 3D model design of our big wagon. It has some key features, such as high quality spigots, which are on right height, so people don't need to bend. Also, it's on a double X trailer. It has a static rounded design, and it also has a lot of space for running. Next, you can see inside of the power tank. Basically, we decided to go with 3 of them, 3 IBC tanks. Each is around $300, which gives us a less expensiveness, and it's self-leveling, and also they are more convenient. Next, Kenzie is going to explain you more about bill of materials.
Thank you, Ante. Here we have our bill of materials chart, and it's basically gives us the general idea of the materials we would need in order to construct the full-size version. When reading this, you begin at the bottom and you make your way up to the top. And we also added a color code so it would make it a little bit easier to see which materials go into making which subassembly. First, we have our housing subassembly, and that has the sheets of stainless steel and then the door. And then we move over to our plumbing subassembly, and that has the water pump, the tanks, the spigots, the copper piping, and then the water meter. Both of those subassemblies come together with the wooden trailer to make the structural subassembly. Then we move over to the cooling subassembly, and that has our custom-made water cooler and then pipe mount. And that in turn combines with the generator to make the power and cooling subassembly. Now, at this point, we would combine both of the two main subassemblies to make a functional wagon. At this point, we had a working wagon, so it would distribute water and everything, but we decided to also add in the branding and signage. As you can see, where it would make it more aesthetically pleasing and it would achieve our goal of community outreach. Here we have our budget for the big version, and it's basically just a projection of what we would think it would cost to build each of the systems of the model. Our housing system would cost around $3,100. And then the plumbing would be $1,250. The trailer would be $3,700, and then the cooling would be $510, and the power would be $1,000. That all totals up to be a little over $9,500, which is within the budget of $2,000. Next is Ante to talk about our main model design.
As Kenzie mentioned, this is our 3D model of our mini design. You can see actually what we built here. So it has a cart which is 800 pounds capacity. Our whole system is 150, which includes 90 pounds of water and all other things like PVC, 2x4s, housing, etc. Also, it has two tanks, each 5 gallons, which gives us, it can serve 76 people, assuming that each person is going to drink just one water bowl. Also, it has 4 spigots, but actually only 2 are working because it's just for testing. And then it has a basic housing, and the spigots are the same height as for the big one, and it has the same, pretty much the same plumbing system as the big one. As you can see, we have 2 doors. Those are basically for refilling tanks, activating wall valves, and replacing water cooler. Here is our schematic. As you can see, we have 2 tanks. Then all yellows are adapters. Blue is PVC. Black are elbows and these we have pump. We have also these 2 red ones are ball valves, and then check valve. Check valve makes sure that water is coming in the right way. And then ball valves are for external feed. If we want to use, if we don't want to use tanks but just external feed, then we just close this one and open this one. Also, we have water cooler. Actually, on this prototype, since we didn't have enough time, we have everything documented, but we didn't actually put here a cooler. But it would basically be a big box full of ice with a PVC pipe going around in a circle, so water can stay inside the cooler as long as possible. And then we have a water meter to check our flow rate. Also, this is 2x4s, which are surrounding the tanks, and it gives us more safety. On the next one, you can see just the side view, how our PVC is going up to pipe to spigots. And in this model, we included the connectivity, which gives us like option of removing tanks and then removing housing and then refilling tanks. Next is Kenzie again with bill of materials.
Here we have another bill of materials chart. This time it's for the mini model. So it's very similar in the way that it corresponds to different subassemblies to as the big model, but this time it's a little different in the materials that we have used. Such as for the housing, we use plywood and screws instead of stainless steel sheets. And then for the plumbing, we used plastic tubing instead of copper pipes. And just like last time, both of those subassemblies combine but this time with a wagon instead of a trailer to form the structural subassembly. And then the power and cooling subassembly is the same exact. However, we did not include the cooling system. And then both of the two main subassemblies combined to form the functional WaterWagon, and we did add the branding and signage component to make it a completed WaterWagon. Here we have our parts list and budget for the mini model. And as you can see, the list is pretty extensive because it shows each part that we have bought to make the model that we brought to you today. This spreadsheet also shows the different, the quantity of how many we got, and then where we got it from, and then the cost of each of them. And on the far right, you can see that's our running total for how much we've spent, and it begins in green because that indicates that we are well within our budget. And then as you go down the chart, it changes from green to yellow, and then we stop at orange. But if it went all the way to red, that would indicate that we were at our maximum budget or we had gone over. We originally budgeted $1,250, but luckily we only spent $860, which meant that we reduced our cost by 31.2%. Here's our process flow chart, and it gives us the basic overview of each step we've gone through throughout the project. So, and we also added in color code to make it a little bit easier to understand. So the green is the start and end of the project. Yellow indicates a deciding factor. And then the white box are a different process that's taking place. So we began to start, and that's where we came up with the different designs that Aaron mentioned earlier. And we narrowed it down to one final design to move forward with. And at that point, we began to order parts and gather our materials. And once they came in, we fabricated the different subsystems that I mentioned in the building materials. Once that was finished, we brought all of the subsystems together and assembled them on the mini wagon. And once everything was complete, we began testing the different subsystems, and that's where we come upon the deciding factor of whether or not the data is satisfactory or not. If it's not, then we move back to reviewing the design, and we would go all the way back to the beginning and establish a new version of our design. And if it was satisfactory, then we documented our data and recorded it, and that's where we come to the end of the project. Here we have our mini model fabrication steps, and as I go through, a green check will pop up to indicate that we have finished a step. First, we begin with ordering parts, and then we move to laying out the mock setup in reference to the schematic that Antair talked about. And then we begin to dry fit all the plumbing. And that's so we could get a feel for how we wanted it to look and make sure it was still functional. And then we began to build the internal skeleton. So that has our power and our plumbing subassembly, and it also has the water storage units within it. Once we finished that, we began to glue and assemble and install all of the plumbing within it. And to finish it off, we added the protective housing on the outside to encase all of our functional aspects of the WaterWagon. And since we had a little bit of extra time, we decided to add paint and other branding components. So it would resemble what we would want the big model to look like, and so it's more aesthetic. Now I'm going to hand it over to Justin to talk about our fabrication testing.
These are final skeleton. This is what's inside the WaterWagon. Right here, down below, you can see a water pump, followed by 2 5-gallon tanks. Below the spigots, you can see the quick connectivity, and below the quick connectivity is the 2 spigots. This is just a comparison between the schematic paint I drew up and the real life internal skeleton. Again, you can see the 2 5-gallon tanks, followed by the pump, the 3 valves, and the 2 spigots up top. This is our pump. You can see 3 valves. The cool thing about this pump is you got 3 valves. You can close one and more water go to the other spigot, or you can open both valves and the same amount of water go through both spigots, or you can close both valves and no water will go throughout the spigots. On your right here is the water meter that will record how much water is going through the system. And at first we started with no branding on the side, no paint. Mackenzie and Auntie did a fantastic job putting together the citizen logo and spray painting the whole WaterWagon. This is Ante testing out the plumbing. Now, he is going, putting water through all out the plumbing system to see if there's any leaks or if we need to glue anything back together. The reason why the two PVC pipes are going back down to the 5-gallon tank, we don't want to cause a mess.
We were pretty excited when it worked for the first time.
This is spigot test. We are just testing to see if water actually come out the spigot, to see how fast it come out and how powerful it come out. And this is the two spigots with the quick connectivity. The cool thing about the quick connectivity is you don't have to untwist the two spigots and get the housing off. You can just pull the housing off with the spigots and clean inside and refill the 2-gallon tanks. And this is our final prototype. We put 2 doors on the side for easy accessibility, and you can see inside the water. This everybody with the final prototype, and that's paying with testing.
Thank you, Justin. So I'll be going over some of the testing. Basically, we just did these tests to validate that all of the functional components worked and we're at desirable levels for what we wanted. So first test we did was the flow rate test. This is determining how much water is coming out every second. So what we did is we filled the 2 5-gallon tanks full of water. We ended up only testing 3 trials of 2 gallons, so we really only used 6 of those gallons. But we recorded how long it took for 2 gallons of output to come out of water, and 2 gallons is around 256 ounces, and each one of our trials took about 55 seconds. So if you just do a simple proportion, you can find how much it takes to fill just 1 water bottle. So if 2 people walk up to the WaterWagon at the same time and they both press the spigot, which takes more pressure, then they can both fill their water bottle in a total of 7.4 seconds. If one person walks up and fills their water bottle, it's more pressure just for them individually, so it takes around 5.5 seconds. So here we did a cup test. We just wanted to make sure that our flow rate calculations were actually accurate. So we just basically timed how long it took us to fill 1 water bottle. And in this test, you'll see it was 5.45 seconds is what we got. So that was very accurate to our flow rate testing, which was less than 1% error. Next, we wanted to do a meter test, and this, we just wanted to basically verify that our water meter worked. We took a 4,000 milliliter Erlenmeyer flask and filled that up 8 times to fill the tanks. There's another way you can fill up the tanks that's more convenient, but we wanted to make sure we knew exactly how much was in the tanks. So that's about 8.45 gallons. And then we completely emptied it all the way until there was nothing in there. And then the water meter read around 8.6. So our water meter was around 1.7% error, which is pretty accurate for what we're looking for. So some next steps, the big phase of the project is still yet to come with the big model, the full trailer size that could be used for more people at larger events. But improvements on our design that we could do now is, unfortunately, we were not able to get the water cooler working in the scope of this project for the miniature model, but we do have a lot of documentation. We worked with Dr. Sarker on a lot of thermodynamic calculations for the cooling process. We'd also like to add functionality to the other 2 spigots. For our demo here, we just had the front 2 spigots working, so we could pretty easily connect the other 2. We just did 2 for testing purposes. We'd also like to muffle our pump. The pump on the inside is pretty loud. We had trouble. We did order 1 pump, but the day it was supposed to arrive, we called the company and they said that they're out of stock. So we had to get a different pump, and it has a little noise to it, so we'd like to muffle that if at all possible. We'd like to add drip catchers for the spigots, so just in case you accidentally press it, or if you take your bottle away too quick, that doesn't drip on the ground. A more convenient filling method. Right now, we're pretty much just using taking off the housing and using a hose to fill the tanks. If we could find some other more convenient way to fill, then that would be nice. We're thinking it could be possible to hook up a hose to the external feed and back run through the pump into the tanks. That'd actually be really nice because the external feed is like the first thing you see when you open the back door. And then we have a check valve on that external feed to make sure that water isn't going back into whoever system is filling it up, because we don't want to contaminate whatever the main water source is. And then also some sort of drainage system. Currently, you either have to somehow find a way to dump the tanks or just remove all the water through the spigots. So better draining system would be a good improvement for the future. And then finally, we have some project takeaways. Each person is going to kind of go through and say what they learned through this project and just kind of soft skills that we've learned. We've learned a lot of engineering concepts and technical information, but sometimes it's nice to go over the soft skills that we have learned. As for me as a project manager, I've learned a lot about delegating work, and if you don't delegate work, not everything runs as efficiently as possible. Definitely a big skill. I've tried a couple times where I've tried to do too much myself, and it's not as good. It's better when you can highlight each person's specialties, because everyone has something to contribute. And then also team synergy. Some days you have obstacles and a lot of things that go wrong, and you're not feeling like you want to work that day. There's a lot of different things going on, but if you just have that positive attitude, it kind of helps the whole team have a positive attitude, even if you don't really feel like that on the inside, and then we can kind of build off that to make more progress.
My first is overcoming obstacles, and that's because our team faced our fair share of them. But we did overcome them together with a little bit of teamwork and problem solving. And then my next is that I realized it's very, very important to utilize every resource given, whether it be other team members or even the faculty or even your guys' staff, because each person plays a specific role in getting the
For me, as an international, it was a big thing to work with you as a real world company. I feel that it gave me more confidence for the future and what in the future I can expect. Also, I would point out the teamwork. I feel that every person has something unique to show and can contribute in our project.
My biggest takeaway was kind of what Kinsey said. We faced a lot of problems we didn't see when we were planning this design. None of us were plumbers, so we had no idea how to Thankfully that we had Dr. Stokemeyer. He helped us really with plumbing instead of Dr. Plaga. We also learned, or had to learn how to adapt to these situations. We used to make a space for all it's worth.
My biggest takeaway is teamwork. We couldn't do it alone. We had to work as a team, build this WaterWagon. And my second takeaway is trusting your team members to do equal amount of work, so we can get it done on time.
Next, I just have a couple acknowledgments, starting out with Dr. Twiga. He helped us as our faculty lead. A lot of the time, he did a lot of work on our housing, so we're very grateful for everything he's done for us. Next is Dr. Steve Spickelmeyer, also helped us a lot in the fabrication stages. He did a lot of Home Depot runs. You saw how big that list was. It's not like we all got it at once, so we really appreciate everything he's done. Dr. Spickelmeyer, Jose Sanchez, program director, just facilitating our relationship with you guys and starting us with the project. Dr. Sarker, he helped us a lot with the thermodynamic calculations for the water cooler. So fortunately we do have that documented for the future and the bigger model. David Olawale, thank you for instructing the course, and kind of when we feel like we can't do it, he kind of tells us that we can and pushes us to keep going. Of course, Lisa Valiato, she's definitely helped us a ton with all of our purchasing and financials, and put up with us when we forget receipts. And finally, of course, Citizens Energy Group for all of your guidance and funding. We definitely would not be here with a nice prototype without everyone on this list, and I'm sure I'm missing a couple people, but we just want to thank everyone. And finally, I guess we'll show you how the prototype works. Unfortunately, we haven't flushed the entire system completely since our fabrication, so we won't be having anyone drink any of the water today. And also the pump is a little loud, so just brace yourself. So the spigots that are working, there's 2 on this side and 2 on that side, and then the front 2 spigots work on both. So on this side. And then we also do have the ability to throttle how much pressure is coming into those spigots by turning off and on. There's just a couple of valves right by the pump, so we can close those a little bit. We have a loop that goes within the pump to kind of reduce some of the pressure, because the first time we tried it was kind of just like, like crazy. So we did have to throttle that a little bit, so we can change that, which is nice. But yeah, that's our prototype so far, and the floor is